Building on parameterization, we now include vectors. So remembering a vector is a push. It's a push from one point to another, and no matter how you get there, it's the same vector. So if I'm pushing horizontally, that's called I, and I'm pushing vertically, it's called J. So if I push horizontally 3 I's and vertically 2 J's, and I get to the same point, then it's the same vector. So that vector is 3I plus 2J. This is the only algebra for vectors. When you add them, you just do successive pushes, and when you scale them, you just multiply by a constant. These are called scalars. The reason why it's a scalar is it is a number, but it doesn't have to be a real number. It's for other more abstract courses. Going back now to parametric functions, you have some function that's all loopy, or you just don't want to describe y as a function of x, so everything is described in terms of a parameter, t. So every point on the curve has a t value. If I start from the origin and point to that point with a vector, then I'm pushing x of t over and y of t up. Starting at the origin and pointing to that point is a special kind of vector. This is called a reference vector. What we're concerned about is calculus, so let's look at the case where we're at a point and we know the slope. So we will know that the curve is a little straight line piece at that point, and we'll extend that line piece into a line. So I want to describe any point on this line. So I know a point, say we're at parameter value 2, and from the last video we know the slope, dy dx at that parameter value, which is y prime over x prime at 2. X prime and y prime are functions of t, so derivatives in t. Plug in the point slope equation for the line, and there's our tangent line. What we'll do now is solve for the y and x components. So I'll collect the y components together and collect the x components together. They're always equal, so there's always equal some number, say tau. Now I can solve for x in terms of tau, and I can solve for y in terms of tau. This gives me a mapping, tau going to xy. So every point on this line now has a tau value. Tau equals 0 initially, and general tau otherwise. Default naming convention. These are x of tau and y of tau, which are both lines in tau. So now let's look at a specific value, tau equals 1. So now I'm 1 unit along the line, 1 tau unit, which is an x prime y prime change in the coordinates. This is perfect for vectors. Start at the origin, push onto the line, start at the origin, point to the other point on the line, and write down what we're looking at. So the pushes are the coordinates. Break apart and recollect my pushes. I'll collect my x and y pushes and my x prime and y prime pushes. this vector is called the tangent vector, because it's the vector that connects tau equals 0 to tau equals 1. This initial vector is called the position vector. So in particular, the position vector for t equals 2 and the tangent vector for t equals 2. So t is the parameterization for the curve, tau is the parameterization for the tangent line. They're different parameters because they're different objects. And then any other point on the line I get just by scaling that tangent vector. So this is another way of thinking about how to describe objects. So putting it all together, I'm on a curve, I have a parameter value, position vector points to that point, and then the tangent vector is pushing along the tangent line at that point. This is a very useful schematic, and we use this quite often in physics and mathematics. This is kind of the basic building blocks for all parametric ideas.